So let's get started. Do you remember when GCSE changed in 2018? We had this question which really flummoxed students who were expecting to see osmosis in the context of potatoes, but those nasty examiners decided to switch it to talking about carrots instead. They claimed that was basically the only change, but yet that was enough to throw students who were confused. So this became a kind of poster child for a problem that is hardly new, but is now more important than ever. You can see in these examiners' comments, they're always complaining that students can't apply their knowledge, right? It's easy to say, I remember when I was teaching, writing reports, saying the students know things, but they can't apply them, as though that was actually a very useful comment. I regret that now. And what we want to do now is figure out, using Blueprint, what that actually means and how we can train students to do that. So we're not just stuck with saying these kind of verbal, truisms that have no purpose. And early on in the development, we came across this area of research that we've shown you a few times called expert novice research, which really identifies the difference between the typical student who can't apply and those students who can. And what the cognitive science said was it was all to do with the way their memory was organized, the knowledge organization, in other words, rather than just the amount of knowledge, which is easy to get by just learning what's in the specification. What students need is to organize it in a kind of hierarchical fashion so that the fundamental ideas are at the top and other ideas are linked to them. That kind of way of organizing your knowledge makes it easy to detect what situations mean in terms of what concept do I use, because all these ideas are carefully connected. They're not just sort of randomly connected. There are only a few connections to each idea. So it kind of tells your mind what to do with knowing it's to do with Newton's second law. That kind of links to, okay, is it to do with balanced forces or acceleration or momentum? So when the ideas are well connected, it becomes easier to solve the problem. So we're going to use that sort of idea of turning novices into experts and a load of research on various ways to make problem solving easier and how to teach in ways that make knowledge more applicable. And we've condensed all that down for the sake of what's possible to cover in one webinar into 3 principles, these takeaway ideas with the catchy names. So we're going to go through them one by one, and hopefully you'll remember them and figure out ways to apply them yourself. So firstly, we're going to talk about scaffolding. I guess that's the most familiar one. The idea that we can get students to achieve more with some expert help. They can kind of climb higher and achieve the goal, and then you take away that scaffolding. And one particular way we're going to show you is this idea of teaching strategies to solve problems, cognitive strategies. Then we're going to move on to hugging, which has provoked a little bit of mirth. What we mean by hugging is what the researchers who invented the term suggested, in a sense of staying close to, hugging being kind of metaphor for staying close to the actual eventual performance you want from students, and using that as a method for teaching them. So not expecting that if you teach them in one way, they're going to apply it in some completely different situation, because that doesn't happen generally. If you want someone to apply something, then it makes sense to teach them in as similar ways as you can to the way you want them eventually to perform. That's hugging. And bridging is the opposite, really, is saying, okay, so if it is difficult to apply, what kind of heavy guns can we bring to this situation? And the best thinking is really that you've got to understand the deep structure, in other words, fundamental ideas of that topic. And if you know them at an abstract level and you can connect them to these situations where they're useful, that's the way to solve problems. But that, of course, is the most difficult strategy, so we'll deal with that at the end. I hope that agenda seems useful. Gemma, do we have any questions?
Nope, not yet.
Okay, well, Gemma's going to introduce the first strategy, and in each strategy we're going to show you examples from the course we've created to put Blueprint into action.
Yeah. Okay, so I'm going to look at scaffolding. So there's a couple of GCSE questions here. I'm just going to give you a bit of time just to have a read through them and think about how you would solve them. So what thinking process would you go through to solve each one, and consider what the difference is in that process between the two questions. So I'll give you a few seconds just to have a look through and have a think about that. Okay, so let's have a look at them. So for this problem, this physics problem, there is a procedure, a specific procedure that you would go through in order to solve this. And it's specific to the content. So that's why it's called a domain-specific strategy. So given another similar question, you can go through the same procedure and get the correct answer. So I've put down the procedure there, 4 steps. So you would identify that that's the wave equation, remember the wave equation, rearrange it, substitute the values, calculate the answer. So if another question on the wave equation came up, or even one which is a different equation but still the same procedure, then you would follow that and get the answer. So obviously that's one powerful strategy that you can teach, a strategy on how to answer similar questions to that. So any kind of science idea that is a quantitative science idea, you can use similar steps, but obviously not all science ideas are. And that's when we come on to the second question. So this doesn't really lend itself to any kind of domain-specific strategy like the first problem. And that's because it involves connections between lots of different concepts. So it's hard to provide a general strategy. So in this case, you can fall back on a domain general strategy. So you would typically think about what is the problem asking you to do, what's given, what's unknown, thinking about what I already know about the topic that will help me solve it. That's a general thinking that you would go through. And we've turned this into our 3-step strategy that we use in our practice books called Detect, Recall and Solve. And that could be used with any content at all. So why do we teach these cognitive strategies then? Well, it's easy to figure out that most students can't jump from content to figure out how to problem solve themselves. So we need to teach them some strategies that they can use, both domain specific and general strategies. And to do that, what you can do in the classroom and what we've done in the practice books is to provide scaffolding. So this is a way for novices to achieve that goal with a bit of help. And this is supported by what we know by Vygotsky's zone of proximal development. So we are giving them just enough help to get them to move on to that next step of problem solving independently. And metaphor about scaffolding is also based on some research by a psychologist called Jerome Brunner, and he said it was a temporary construction to help students to reach that higher up task. And what we've done is use worked examples, and this is what you'll find in the practice books. We've got about 30 to 40 problem types which cover all of the key concepts in a different year. And by going through a worked example with the students, you're modelling how to use these cognitive strategies. Whatever problem you do, it should be domain specific, so it should relate to the key concept. And importantly, the type of problem that you use should be similar to the ones that they're going to come across in exams, because we're training them on how to answer these kinds of questions in exams. And these are the AO2 questions we're talking about here. So to write these practice books, what we did is we looked at loads of different past GCSE papers from different boards, and we spotted the types of questions that come up again and again for each key concept, and we based our problems on these. And again, there's lots of established cognitive science research to back up why worked examples work. So it's particularly going to benefit the novices, better than just giving them loads of problems to practice independently. That's because by using a worked example, you're reducing cognitive load. So for a novice, the biggest challenge of these problems is that they've got lots of content here to remember and recall, as well as the strategies that they need in order to process that information and to write the answer. And this is going to fully overload their working memory, so they can't actually store much in their long-term memory. So that means that students can just about manage to do the problem, but they're not actually going to learn anything from it. So if you do a worked example and you go through a problem with them, most of the thinking therefore is done for them. And so they're able to actually process what's going on and use that information when they come to do a problem independently. So let's have a look at an example of a problem then. This is from our practice books, and also it's on our online courses. And it's going to show you how you can teach both domain specific and domain general strategies when problem solving. So here's the question. It's a GCSE, based on a GCSE question about types of cell transport. So let's have a look at the strategies you could use when you're going through this worked example. So the first thing we're going to look at is a domain general strategy. So you can use this with any content, and it's how to do the detect stage. So the steps that you do in the detect stage. So first step's obvious. You read the question. Second step, you need to find the key information. So you can model this with your students by highlighting where you think the key information in the question is. Also, you can take the steps that you would use to interpret a table, for example. So this is domain specific, because a lot of questions on cell transport like this, also so diffusion, active transport, osmosis, you quite often get tables like this. So if you can model the processes that they need to take to analyze tables like this, then you're going to help them in similar questions. And we also find it's really good to show how you can visualize data using diagrams. So we've got a diagram here showing the roots and showing the different minerals around the roots, in the roots and in the soil. And we can actually model this, go even further and model this at a particle level. So we can actually show how you can visualize the differences in concentration of particles between the soil and the root as well. And then the next stage of detect is to identify the unknown. So where in the question are they asking you to figure out something, and what do you need to figure out? And then finally, the last stage of detect is where we decide the key concept. So what key concept is going to help us solve this problem? And in this example, it's cell transport. So we'll be looking at diffusion and active transport. Now that step's important because in the next stage, in the recall, we're going to recall everything we know about active transport and diffusion. And this is, so recall is another example of a domain general strategy. You would use this in every single problem you come across. We're going to think of the key information we need. And in the recall, analogy is a really good tool to use. So this example here, domain specific, is talking about concentration gradient. So we use this model to explain concentration gradient, and that could be used in lots of different questions on cell transport. So the model we use is thinking about a ball rolling down a hill. That's light diffusion. It's a passive process. We're going from high to low concentration. But obviously we can't go from high to low to high concentration, because that would be like a ball rolling up a hill. That requires energy, like a person pushing up the ball, and that's active transport. Okay, and the next stage is the solve stage. So this is the third part of our domain strategy, which is showing you how to structure an explanation using these 3 stages: claim, evidence, and reasoning. So you can model to the students how you can structure an explanation in these 3 steps. So the first step is making a claim, which is a simple statement that answers the question. Then you have the evidence. So this is data or observations, which is going to back up our claim. So this evidence in this case comes from the table. And then you've got your reasoning, which shows how the evidence supports the claim. And that's where you bring in your understanding of the key concept. And we're also using there the inquiry skill of making an argument as well. So I described scaffolding earlier as a temporary support to help students perform a task successfully. So if it's temporary, there needs to be a process in order to remove it, and this is known as fading. So we can have a continuum from complete scaffolding, which is the worked example, down to independent problem solving, which is what we want students to achieve ultimately. But to get there, they have to go through a series of steps. Now, depends on the students. You might have to go from one step to another. Some students, you can miss out one of the steps. So I'm going to show you the examples we've used in the practice book and also in our online course. So after the worked example, students have a go at an isomorphic problem. And that means it's very similar to the worked example. It follows exactly the same steps. So you can see here that problem, we've got a table, like in the worked example, but it's in a slightly different context. They should be able to answer it following the same steps. Now, some students won't be able to go straight on to solving that isomorphic problem. They might need a little bit of scaffolding in between. So here we can use the faded worked example, which partially solves that problem. So, for example, you could give them the detect, and you could give them just the headings for the recall for them to fill in. And the solve, you could write it out with just some missing words for them to fill in. So you're giving them the worked example with bits missing this time, which is slightly more difficult than obviously doing the worked example for them. And then the students get more practice by carrying out some problems independently. So we have a total of another 3 questions in the book. They all have the option of using hints, so that's a little bit more scaffolding. And then also the final question as well is also a bit more challenging, which is there to extend the students that are ready for that. Okay, that's that section.
Thanks, Gemma. I think we've just got lots of teachers absorbing all of what you said and a bit quiet on the chat. So I'll move on to the next section. So Gemma's shown you direct strategies for problem solving. What I'm going to do is take you into a different area and look at 2 particular ways of helping with this problem, which we're going to call transfer. Hugging and bridging being the 2 strategies. So what is transfer? For the last 100 years or so, people have been debating how it is that students know stuff, but they can't apply it. So carrot gate is hardly new. It is really the goal of education, after all, to teach things that can be used in the real world. After all, if you could only just parrot back what you've learned, it's hardly very useful. So transfer means taking something learned in one situation, and that allows you to perform better or learn better something else. We take that for granted, of course. I mean, you know, when you read one book, you can read a different type of book. You can kind of go into one restaurant and know what to do based on your experience of other restaurants. Transfer does happen in everyday life in some situations, but apparently not very easily with science concepts. So the researchers that have looked at this and came up with these nice words, hugging and bridging, came to the conclusion that there were basically two mechanisms in your mind that help with transfer. The first one we're going to look at is the easy method. They called it low road transfer. This is what happens when you've been driving for many years and then you suddenly switch countries and you take a car with left-hand drive. So that might cause you a few problems for a few hours, but after that, it's pretty easy to make the adjustment. So this is what you might call automatic transfer. Your mind figures out very quickly how to adjust what you know, your skills and knowledge for this new situation. And the way it does that is because it just looks for similarities between the old and the new. And once you detect all those, you kind of operate your existing programs, and that gets you through the new situation. So that's what we want wherever it's possible, because that's the easiest kind of transfer to achieve. How do we do it? Their main strategy from the research, they called hugging. And what they're trying to do is essentially say, well, transfer happens best when there is the maximum similarity between the way you learned and the way you have to perform. And I'll give you an analogy for that. Because actually in science, I feel that we don't take advantage of this very much. We train students in a kind of theoretical, abstract version of what science was done, you know, and what we found out. And very occasionally we give them experience of doing science for themselves. Most of the time they're just kind of force-fed the products of what previous scientists found out. Now you can contrast that with the way that music or sports are taught. And here's the example from football. So to prepare students for playing 11th side football, current wisdom suggests that they spend most of the time working on small versions of the big game, right? Previously, in many countries, there was a lot more sort of just skills and drills practice, but things changed, as I understand it, when the people went to Brazil to figure out what it was that made their players so great, and they discovered that it was a particular kind of game called futsal, which is a sort of souped up five-a-side game with a heavier ball and a set of rules that favor players acting really fast, developing strategy and skills because they're touching the ball so often. And they realized that we should be training our football players in the same kind of way. So in other words, they're spending more time in a similar situation to the real game. That doesn't mean it's the same. That doesn't mean you start 7-year-olds on a full-size pitch, but you start them on a small, simpler version of the game rather than something that's actually completely different, like just doing skills with cones. Obviously that is necessary, but the problem with just doing the skills and drills, an analogy there would be to science, the problem with just doing lots of, you know, principles that you learn from the board and you solve some routine problems in your textbook. Problem with that is that it's quite divorced from these apply situations, and we get this idea that this transfer just doesn't happen. And that's what the sports people figured out, that the students weren't able to transfer to the real game what they were learning in these artificial skills and drills. Whereas if you construct a kind of small-sided game version of the big game, then students are sort of playing football all the time, but practicing the skills within that environment. That is I think I've summarized it, a more modern way of sports coaching. And I think we should take the lead from what they do really well and apply that thinking to science. So what does that mean? Well, we've tried to put that into practice with our course, and you can see in Blueprint, as Gemma was about to show you, that what we're creating is not just artificial learning objectives, but a kind of progression of ways to sort of do science right from the beginning of the topic, rather than leaving it to the end and the apply questions. We want students to be doing science, solving problems, in other words, right through the topic. Gemma will explain.
Yeah, so I'm going to explain this in the context of this key concept, which is heat and temperature from Year 7 Unit Energy. So this is the understanding, the main idea that we're trying to get students to understand. It's all about temperature difference and what affects how quickly energy moves from warmer to cooler. So let's have a look how we build that understanding then through these 3 stages. So we start with acquire, we go on to apply, and we go on to analyse. And each one of these goals are actually a progression of problem solving activities. So they're all simpler practice versions of the real thing, which is where we want students to be. So whether that is being experts at answering GCSE questions on heat and temperature, or just basically having a really good understanding of this concept. So acquire, we start off, is very structured. Then we move on to apply, which are the problems that I've just talked about. And then analyse adds more complex skills and information to that. So let's have a look at what we develop for each of these goals in turn. So this is what we did for the acquire for heat and temperature. So in the acquires, then students explain phenomena using structured problem solving. So in this lesson, students are set a puzzle. So they're told that a body is found in an icy lake and its temperature is 29.5 degrees C. So they need to work out when the person was killed. So we're giving them a problem to solve, but we're not making them do it all by themselves. We're giving them lots of structure to help them to figure that out. So they do an experiment, and they first think about, well, what variables could affect how quickly a warm object cools down. So we're thinking about what variables could affect it. So that's kind of like the detect stage. So they're thinking, what do I already know that could help me here? Then we go on to an explore activity, which is where they do an investigation. So here's the investigation. So we give them an orange in some water, and we're going to plot the temperature change of the orange in different temperatures of water. And they're going to draw a line graph to show the change in temperature. And we're going to explain all about the concept here and what affects the rate of temperature change. And then in the epilogue, they use all that information then to work out the answer to the original problem. So they're going to use a temperature graph to work out when that person was killed. So this is a very supported version of problem solving. They're given all of the steps of how to do it, and they're guided along the way. So then they're ready to move on to the apply. And in the apply problems, they're presented with temperature graphs again, but in lots of different contexts. So we're seeing, can they transfer this knowledge to new contexts? So they need to explain the effects of one variable on the rate of cooling. And then once they can do that problem, we can go on to the analyse. So the analyse is going a step further. The problem here is more complex. So we need more interpretation and information organisation. And we're placing a higher literacy demand as well. And we're bringing in different inquiry skills into it. So I've put up a little bit of this task. I'll quickly explain it. So they're told that this person heats up their lunch in the morning in the microwave, gets it nice and hot and takes it to work. And obviously it's going to start cooling down. And we don't want that food to be in the danger zone for very long, between 40 and 60 degrees, because that's when bacteria start to multiply rapidly. So what they've got to figure out, the problem they've got to solve is, well, how does he make sure his food isn't in that danger zone for too long before he eats it at lunch? They're given lots of different graphs with different variables which could affect that rate of cooling, and they have to analyse those graphs and help solve the problem, come to a conclusion. So there's lots of information there to take in. We're introducing this whole new thing about danger zones they don't know anything about, so they have to figure out what all that means, have to analyse data and then come to a solution. So you can see here, this is a much more complex problem to solve using that information. But by the time they get to the analyse, they've had lots of steps along the way to help them to be able to solve that.
Thank you. So that's quite a sea change, really, in thinking about what is the environment for learning. I wonder if you'd like to raise any questions in the chat about this. So we're shifting things away from just saying, okay, teaching is about presenting and then you solve problems at the end, to saying, actually, we're going to be solving problems all the way through. Now, in theory, of course, you should therefore have a lot more experience as a student with the kinds of problems you're eventually going to meet. And this is hugging. It kind of makes sense that if you've been solving problems all the way through, you're likely to find yourself more able to apply your knowledge. That's not to say that we're not doing everything you would expect with direct teaching of the knowledge. Yes, we're doing that too, but the problem-solving environment gives us a lot more extra potential to teach the kinds of contexts that we want students to be using, that they're thinking about explaining with the concepts that they're learning. So in other words, they're making these connections that experts have between what they know and the situations to use that knowledge. And also, of course, this is the right way to bring in inquiry skills, because there's an actual need for them when you're trying to think through what experiment to do or what that data means and how can we use that to solve the problem. So this is a much more kind of holistic way to teach science. The drawback, of course, is that you have to come up with these simpler versions of the problem to use as teaching material. And so it is obviously a little bit more challenging as the teacher, rather than just presenting the PowerPoints with the content. So that's our strategy for the low road transfer. In other words, making things as familiar as possible during the teaching so it becomes easier to apply it. I said there was a more difficult route, and this is known as high road transfer. What's the difference? Well, there are a lot of situations where we want people to transfer their knowledge to things that are really quite different on the surface. So let's say you've been learning chess, right? And then later on you come into politics. They seem completely different disciplines on the surface, but underneath, of course, there's a common element really of strategy. If you've learned to play chess well, you understand concepts like controlling the center, and probably there are very similar concepts that are useful in politics, so that if you've been a reflective chess player, then you may well find that you can do politics more easily because of all that accumulated wisdom and principles that you can transfer. But the point is, of course, that transfer won't happen necessarily so automatically. You've got to reflect, you've got to put in the mental effort to see the connections between two different areas or situations, because they're not superficially obvious. And of course, that's a little bit like the challenge with students meeting the carrots problem, right? To them, the situations look completely different. They think they've never seen that before, and they complained on social media how can they do that and give us a completely new situation? Whereas all the teachers were thinking, well, it's exactly the same thing. We just changed some superficial information about a root vegetable. So actually what we're saying here is that the important thing to teach is the underlying deep principle rather than what's superficial in terms of the context, the vegetable. The underlying principle of it's a cell, it's got a semi-permeable membrane, and so we can have these processes like diffusion operating. The students may not have learned that. They may have just learned some knowledge relating to what potatoes do, and if you put water in, this is what happens. They haven't actually figured out this abstract principle, and that's what high road transfer is saying. We've got to teach more deeply, and students have got to see these patterns and principles, not just the superficial knowledge. And the strategy we're going to recommend for this is called bridging. To create this bridge between different situations, we're going to build a strong, deep, abstract idea. And of course, as we all understand, that doesn't come from just telling people stuff. They need to experience it. Students need concrete experience. And from that, they can abstract these ideas. So we're going to be heavily into things like bodily and visual analogies, because that is really how people think. And we're going to use those as a kind of stepping stone to building the abstract idea. And then we're going to try hard to make students generalize and see the commonalities across different contexts. So how do we do that? There's a particular area of research which I find very interesting, because it helps us to go beyond these, debates between inquiry and direct transfer and realize, in fact, that it's both that we need. We need students to think, to do some form of inquiry, of course, because that's actually how they reflect and process things. But of course, we can't expect them to learn everything on their own. So we do need to tell them stuff, explain it, make it very clear, save them the time, make sure they're following the procedures accurately. So it's a false distinction. What really matters is when you do one, when you teach by telling, and when you get students to figure things out for themselves. And this area of research helps us to think that through better. So I'd like you just to look at the yellow highlight. Has anybody come across this research? It's about 20 years old, and it emerged out of some earlier experiments where these researchers were saying, does it matter when we tell students the stuff? In other words, should we start with the concept and then just get them to practice it? Or should we give students some experience with the phenomena first and then tell them what it means, right? And they decided that the evidence pointed to the students having concrete experience first, which sort of prepared them for the theoretical explanation. And if you've been to any of our webinars, you know that we've been following that principle in everything we do. So here is the more detailed later work that looks at why it's useful for students to experience things first. That doesn't mean that we're giving them total discovery learning by any means. We're giving them quite a lot of guidance, but we are delaying how much we tell them until we think they're ready for it. So I want to tell you how, with a particular example, you could do that. Let's take density. It's a nice concept because it's got quite a lot of difficulty. So the mathematical, the relationship between mass and volume is not a simple quantity that you can measure. You have to do that ratio thinking. and proportional thinking makes it a higher level concept. And of course, students have some misconceptions about density that they come in with too. So knowing that, that would tell you that this is going to be something they're going to find hard to apply. I don't just mean doing the equation, putting in numbers, I mean using density in some situation where they have to figure out qualitatively, you know, what it means to have the same material, different volumes or different masses. They need to understand that kind of thinking. And what the researchers said was, okay, if we want them to get a deep abstract idea of this property of matter, this ratio of quantities, let's see if we can develop this in a concrete way through analogy and get the students to think that through themselves before we present them, you know, with the final finished equation. Because they believe that by doing that, we deprive them of that opportunity to make those connections, and that they would just kind of learn the equation as some procedure to follow without thinking too much. So we took that idea directly in our own course in the way we taught density. So the analogy is that we imagine that there are clowns going in buses, and we make this kind of real so that students can imagine what this is like. You know, there are happy clowns and there are unhappy clowns when the buses are too crowded. And what we're trying to do is create some kind of index, some measure of crowdedness so that we can make sure that the clowns are happy, right? It's got absolutely nothing to do with density at this stage, though it does follow an introduction where we talk about materials. You can see that the question of the explore stage here is, why are some materials heavier than others? So we have introduced the problem. We have given it context. They have held materials. They can see that they're different in terms of which ones are heavier for their size than others. What we're trying to do is now answer the question of why. And we let the students into the secret that we're actually going to help them do that with this analogical thinking. So the first principle that the researchers recommend is the use of contrasting cases. In other words, to help students notice things that are different between two situations or more, because that's actually quite easy for people. We can all spot the difference. We can use our perception to spot things. So we give them different buses and we get them to think about which one's more crowded than the other. And the researchers did exactly this. And the students get some kind of intuitive idea of what crowdedness looks like when it comes to objects inside containers. And you can probably see that the next stage will be transferring this to particles inside boxes, and hence to the idea of density. But there was another principle that they were using that turned out to be very important, which was not just getting students to compare, but to actually think about what was the rule here to determine crowdedness. So in fact, they're inventing this measure of crowdedness. It's not very difficult. It's not like they're inventing Newton's second law. They are just kind of going, well, can you see that it's got something to do with the number, but not just the number, it's the number in one particular box. So in a sense, they're using an intuitive idea of ratio. It's the number divided by the number of boxes. And a lot of kids would be able to do that with some prompting. So having invented a kind of simpler version of the concept themselves, we can take them through to particles and boxes and then lead them towards this idea that density is the same sort of ratio of how much stuff within a particular volume. And once they've got that kind of quantitative idea, having an equation means that they will understand both the maths and the physics. So what difference did it make? According to the researchers, this is an extract from their discussion, worth having a read for yourself. Tell and practice, by the way, is the control condition where they didn't do all that. They just told students the density equation and gave them problems. So they found that students who had to do the inventing and the contrasting cases work were actually better than the students who've been told things up front. And that's possibly counterintuitive, because we tend to think, let's tell them everything because then they know. But in fact, getting students to do more of the thinking themselves seemed to allow them to absorb the theory and the equation better, because perhaps they were making more connections with their existing knowledge, and they were seeing gaps in their knowledge which the theory allowed them to fill. Whereas if they'd been told stuff before they'd even thought about it, that would make it more difficult to connect to their existing knowledge. And it's having this deep and connected knowledge, of course, that allows students to transfer and apply. So if we're teaching for AO2, this seems quite a sensible strategy to get students doing some of the thinking for themselves while they're learning, and not actually making things too easy for them at the beginning. So having presented that idea of teaching for abstract understanding, we're thinking about, have you got the materials to do that? So we really like some kind of feedback on the suggestion that we could produce question sets that would take students through some of this approach, that would get them to look at different cases, compare them, or to think about the quantitative rules. So they're not just going straight onto equations, but they're actually thinking more deeply about the principles. This approach we've stolen from maths. There's a lot of work going on these days in maths that is all to do with the quality of the questions and creating a kind of progression so that students see the mathematical patterns and relationships themselves rather than just doing rote questions. So if you're interested in that, we'd love some feedback or ideas. That pretty much covers our input. So we've given you strategies for problem solving, and we've suggested ways to make transfer easier by adjusting the way that you teach in the first place. Time to stop. Questions from you. Gemma, anything to pick up on?
Not really. People saying that, yes, they like the look of the question sets, which is good, but no questions in particular, no.
Okay, fair enough. Well, we've come to the end of what we planned as a way to help you implement Blueprint. There is a lot more coming. In the last day, we've released some spreadsheets to do with coverage of GCSE in Key Stage 3. We're going to do more of that with planning for how to schedule the units throughout the year and the inquiry skills, and then Year 9 to 11 planners coming later. So you'll have all of that as a framework. If you need any more support, please let us know. If you have questions, you can always get in touch. And if you want to know more about the course that we've created, you can go and have a look on the website. That is on special offer this term. So we'd like to really just say to you, please do act on this as soon as you can so that the ideas are useful. Tell us if you'd like any more support. We are very happy to consider doing any extra webinars, perhaps on some of the practical implications, or to hear from teachers who'd like to share what you've done yourselves in school to a wider audience. But I think that's it from us. Thank you so much for coming.